Last week will be devoted to the gauge series mostly. So application of definition and application of path integral method to quantization of gauge series. But first, we have to deal with fermions, so Dirac fields. And so today, I'm going to discuss the quantization of fermions using path integrals. And the rest of the week will be devoted to gauge theories, mostly non-abelian gauge theories. It will be just an introduction, but I hope you'll get the ideas. Okay, so today, path or functionals integrals for fermions. And I'm going to explain that if you want to define a path integral formalism to quantize fermions, there is similarities and difference with path integrals for non-relativistic particles and with scalar fields, because the fermions obeys anti-commutation rules. And so the mathematical framework to define this is the formalism of algebras or anti-commuting numbers. So these are called Grassmann or exterior algebras, and the rule of how to use this mathematical object in order to do quantum theory, which were mostly, I think, first devised by the Russian mathematician and mathematical physicist called Berezin. So the name of Berezin is also often. Okay. So first I'm going to do some math, abstract math, explain how to use that. And in the second part of the lecture, I'm going to apply this to the free Dirac field. And as you'll see, it will be somehow quite relatively straightforward application of this and of what we did in the previous lecture for the scalar field. Okay, so first, Grassmann algebra. So the problem, as I stated, is that basically fermion operators, as you have seen in the QFT1 course, is that they obey anti-commutation rules. Namely, if you have a Fermi field operator, let's call psi hat, defined at some point x1 in space-time, and another operator psi hat or psi dagger in x2, at some point, if they are causally separated, x1 and x2, instead of commuting, they anti-commute. So when they behave like, in some sense, some kind of classical variables, you don't have to pay attention to the fact that they have non-trivial commutation relation. They still do not behave like usual number. Of course, the anti-commutator is just of two objects, is just defined as AB plus BA. Okay, and that's because of the Fermi-Dirac statistics. So it turns out that if one wants to define a functional integral formalism to deal with fermionic field and, for instance, to treat on the same footing scalar fields, vector fields, and fermions in a path integral formalism, one has to devise such an object. Okay, so what is a Grassmann algebra? So okay. I'm going to define a Grassmann algebra as an abstract mathematical object defined by its generator. So I'm going to consider a Grassmann algebra either on the field of complex numbers or on the field of real numbers, but mostly I'm going to discuss the field of complex number. So this will be, so let me consider a Grassmann algebra of dimension n on C. So this is going to be a mathematical object defined by its generator. So it will be defined by its generators, so set of generators, which is a basis of generator, and of the multiplication rules, and addition and multiplication rules. Okay? And so here I take n, some number, to be associated to the dimension of the algebra. And I'm going to consider the generator to be n generators. So it will be, so I take n generators. In fact, I take 2n generators because I'm going to discuss a complex algebra. So let me call these generators theta 1 to theta n, capital N, and theta bar 1 to theta bar n. So in some sense, this will be the complex conjugate of this object, in a sense that is going to be defined. Okay, so some kind of conjugates. Okay, but you'll see there. Well, in fact, this is a set of 2n generators. Okay, and now, so an element of the algebra over C is going to be constructed out of the linear combination of products of those elements. And we have to define what are the multiplication rules for these elements. Okay. So first, I'm going to assume that this algebra is associative. So like algebra of matrices, if I multiply AB by C, this is the same thing I'm multiplying A by B and C. Okay, and that's associativity is an essential element of quantum theory. If you start to try to define quantum theory with non-associative algebra, it starts to be very problematic. And I think nobody really succeeded in doing something convincing out of that. Okay, anyway. So it's going to be associative like matrices, but it's not going to be an algebra of matrices. So we are going to assume that in the same way that since if two objects anticommute the project of an object A with itself A is if the anticommuter is, it has to be 0, I'm going to assume that the theta A's are nilpotent. So the theta A are nilpotent. So I'm going to assume that in general, some theta A and theta B, the anticommutator of this object is 0. So that's a multiplication rule. It doesn't define exactly what is the product, but it tells that the product of A by B is minus the product of B by A. Okay? And this is going to be true wherever theta A and B are theta or theta bars. So any products, any anticommutator of thetas with theta, or with theta bar, or with theta bar with theta bar is equal to 0. So, okay. Okay. And in particular, this implies in particular that any theta A squared is 0 and any theta bar A squared is 0. Okay, so they are nilpotent. Okay. So these are the generators. So you have 2n generators. And out of the 2n generators, you construct a general element of the algebra. So let me call this algebra Gn, just to remember that it's Grassmann. It's generated by a pair of 2n algebra, and it's over C. So I'm not going to, okay? And so we have defined the generators. We have the commutation rules. And since these objects anticommute, of course, they are less than, let's say, it's not an infinite dimensional algebra. So I'm going to define an element, a general element of the algebra of G, n, let me call it G, as a linear combination of products. So I define G as a linear combination of products with elements C. So these C are going to be complex coefficients. So complex coefficients of products of thetas and theta bars, exactly like in general algebra. But since the generators anticommute, you cannot have more than one theta in the products, well, of each sort in the products, because if you have two, you can anticommute and they go to 0. And moreover, you can always, reorder the thetas using the anticommutation rule. So in fact, you can always order the theta so that we have theta I1 up to theta ik, and then you have theta bar G1 up to theta bar gk. So this is a particular linear combination with k thetas and h theta bars. So I'm considering k thetas and h theta bars. Okay? And in addition, because of the anticommutation rules, you can always, when you have a product of 2 thetas or 2 theta bars, reorganize it so that the smallest index here is to the left. So I can, yes?
So these things are in the canonical, like they're like a classical version of what in the canonical formalism are the A's and A daggers.
No, it's purely, well, it's not quantum, it's purely non-commutative.
Okay. Why do you call theta 1 bar? Why do you call it a conjugate?
That's because I'm going to define a conjugation, and it's not going to be exactly this. So, okay, wait a few minutes. It's just notation.
So it's actually true that theta 1 and theta 1 bar,
they are conjugate, but in the sense of a conjugation law, conjugations, operations that have not yet defined. Okay, so wait a minute. That?
They do anticommute.
They do anticommute. That's what I said. Okay? Theta I, theta bar G is 0. Including when whatever I and G are. Okay? So they do anticommute. Okay, so first, let me define this. Let me go back. So a general element of the algebra is by definition a linear combination of a sum of elements like that, where, so you can assume that first H can be anything, and K k and h goes from 0 to n. Okay? So for instance, you may have 0 thetas. In this case, this is just a pure number. In some sense. Okay, so you have 2n generators, but the algebra contains the algebra of complex number. So if k and h are equal to 0, this is just 1. This is just the number 1 if k equal h equals 0. Otherwise, you have generators with theta. Okay, and then you can sum over the i's, the collection of i's and the collection of k, of g, chi, in such a way that I1 is less than I2, less IK, and G1 is less than G2, less than GH. Okay. So this is a choice. This is, if you want, a choice of basis for your algebra. Out of the generators theta 1, theta n, and theta bar 1, theta bar n, I've chosen a basis. This defines a basis for Gn considered as a vector space on C. Okay? And you have complex conjugations that I'm going to denote C, let's call it I and G, where I, this denotes just this sequence of growing integers going from 1 to n, and G is this sequence of integers. This is a sequence of a growing sequence of integers between 1 and n. Okay? So G, the algebra is a set of all objects of this form. So it's a vector space whose basis is labeled by I and G, so I denote it in this way. And these are the coefficients in this basis. So you have a basis and you have coefficients. So this is a choice of basis which is associated with this choice of generators. Okay? And it's easy to see that the dimension of this algebra over the complex number of my big algebra Gn is just, if I am not mistaken, 4 to the power n. Okay? Because, for instance, let's consider the case n equal 1. We have two generators, theta and theta bar. And theta bar are the generators. And a general element G is just some, it can be a linear combination of a complex number A times identity, if you want, plus B times theta, plus C times theta bar, plus D times theta, theta bar, and that's all what you get. So you see you have 4 elements. A, B, C are complex number. Complex numbers. Okay. 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 And of course, this is an algebra, so you must define the linear combination. So this is an example. For n equal 2, you have theta 1, theta 2, theta bar 1, and theta bar 2. And you can check that you have complex. Here you can have theta 1 or theta 2. Here you have theta bar 1, theta bar 2. So you have 4 elements of this form. Here you may have theta 1, theta bar 1, theta, any combinations, you have 4 combinations. But then you may have some theta, theta bar, because you may have theta 1, theta 2, theta bar. You may have theta, theta bar, and finally you may have theta bar, theta bar. So you may have theta, you may have theta, bar, you may have theta bar, you may have theta, well, I already quoted that, so I'm sorry. You may have this, you may have theta bar, you may have theta bar, but you cannot have theta because you have only 2 thetas, and then you may have theta bar. So finally, those one, you have 4 possibilities. Here you have 4 possibilities, 1 plus 4 plus 4. Here you have 1 theta bar 2, so you have 2 possibilities and 2 possibilities, which is 4. And this one, you have only 1 possibility because you have only theta 1, theta 2, theta bar 1, theta bar 2. So this should sum out. No, I made a mistake. No, this is theta 1, theta. Yeah, no, this is theta 1, theta 2. This can be theta 1. No, I'm sorry. These are 3 possibilities. And here, there are 2 possibilities. And 2 possibilities. So which should sum out to 16. I'm in trouble. Did I make a mistake?
Theta bar, there's 4 possibilities.
Oh, yes. Theta bar is 4. So 4 plus 2. So these are 4 possibilities. And here you have 1, and you have 1 possibility. Okay. Okay, good. Thank you. Okay. So of course, then the product of 2 G1 times G2 is just defined by writing G1, G2, and then reorganize the thetas. The thetas to the left and theta bars using anti-commutation. And each time that you get 2 thetas of the same kind, you get 0, because theta squared equals 0. So for instance, if you have in n equal 1, example, you have G1, which is A1 plus B1 theta plus C1 theta bar plus D1 theta bar, and you have G2 equal A2 plus B2 theta plus C2 theta bar plus D2 theta and theta bar. What is G1 times G2? This is, well, A1, A2. Theta bar, you may have A1 times B2 plus A2 times B1 theta. You may have, of course, A1 C2 plus A2 C1 theta bar. But then which term can you have with thetas and theta bar? You may have B1 times C2, and you may have C1 times B2, but then you have a theta bar before theta, so you must anti-commute, so you get B1 C2 minus B2 C1 theta bar. And that's all, because any further products involving, for instance, theta bar and theta bar give 0, this with this gives 0, because you have twice the same theta, etc. Okay? Yes?
You should always also have A1, B2, and the B1
A1, B2.
B2.
Oh, I am sorry. Yes. Yes. Thank you very much. This was a mistake. Plus A1, D2 plus A2, D1. Yes. Thank you very much. Okay. So you see, these are the games of the rule of the game. Okay. Okay. So, finally, I come back to this, to the question related to what you asked me, which is that beyond I have generators, I have anti-combination relation that defines what are products. So on this way, I can define all the elements of my algebra. This defines the general product relation for this. And now I have to define what is a conjugation. So I'm going to define a conjugation operation that I'm going to call star. Okay. This will be a generalization of the analog of conjugation of matrices. So conjugation of matrices corresponds to transposition for real matrices and to complex conjugation, namely to adjoint. So therefore, you take transpose and then complex conjugation for complex matrices. Okay. So I'm going to define a conjugation operation on my algebra, which is going to be defined in the following way. For a complex number, C star is just going to be the standard complex conjugation. Okay? For generators, as you asked me, theta star of some number I, let's say, is theta bar I, so operations switch between thetas and theta bars, and theta bar star I is theta high. So it looks like complex conjugation. Okay? But for a general element, I need to define the conjugation simply by the fact that if I have the product of two elements, G1 and G2, and I take its conjugation in the algebra, this is going to be the antiproduct of G1 and G2. So I inverse, so the conjugation of G1 times G2 is the conjugation of G2 times the conjugation of G1. So it's like, you see, so this is like for matrices. Okay. Okay. And with these rules, you can easily check that the conjugation of G1 is A1 bar. So with this definition, for instance, G1 star is the complex number A1 bar plus C1 bars times theta plus B1 bar times theta bar. And now what is the conjugate of theta bar? This is theta bar conjugates times theta times theta conjugate, which is theta bar. So this is plus D1 bars times theta bar. Okay? Yes?
I just have a question about the last drill. Is that defined that way just to make the analog with matrices, or is it required?
Well, it's defined for this for the algebra to work.
Yeah.
Okay.
Thanks.
So take it as a definition.
Sure.
Yeah, indeed, that's an analogy. But I don't know exactly the history of that, but this one.
So if you were to define it, say, as G1 star, G2 star, would that be inconsistent with the algebra? Like if you were to define that last real as like the other way around, G1 star, G2 star, would that end up being inconsistent with the anti-commutation rule?
No, this is compatible with the anti-commutation rule.
Yeah, but if you did it the other way?
Yeah, you have, you can do the opposite, but then you will have a different conjugation operation, and you'll run into problem later. So just let me just take this. These are definitions, so accept them or try to work a better one, but there is no physical motivation for that at that level.
Thank you.
Yes?
So what you're saying is that you can do that mathematically.
Yes?
Defining this as
Yeah.
G1 star, G2 star is just not applicable to QFTs.
Yes, it will.
This is applicable to QFTs with this rule, but if you don't swap them,
It will be something different.
yeah, it gives something different.
Yes.
Which is mathematically just as good.
Yes.
It just doesn't have the application of QFTs.
Yeah, it's a different operation. When you have some conjugation operation, for instance, the conjugation in terms of operators in acting on the Hilbert space, you have to see how it is realized in terms of the conjugation in this Grassmann algebra framework. And the simplest representation is using this. So that's what I am choosing this. Okay. Okay, so I have a conjugation. Okay. Okay. So this conjugation exists for complex Grassmann algebra over complex. But in fact, if you try to define, for instance, real Grassmann algebra over the real, then it means that you have no thetas and theta bars. You only have theta 1 up to theta n. You still have the anti-commutation rules. You still have all these definitions, but now the coefficient will be real element. So for instance, a real Grassmann algebra will have dimension 2 to the power n instead of 4 to the power n, if you define it. You are going to have that the conjugation on real number is a standard real numbers. The conjugation on theta will be the theta themselves because you have no theta bar associated, but you still have this. Because of course, it's like real matrices, transposition for real matrices obey these rules, even if they are made out of real numbers. Okay, so this is applicable to real Grassmann algebra. Okay, but that's just a remark at that stage, or an exercise. Okay, good. Okay. So, well, if you are a bit, some differential geometry, you realize that this algebraic rules are at that level exactly the same as the algebra obeyed by the differential forms on a manifold, with the products being the exterior product. So at that stage, we are doing exactly the same thing that the exterior algebra. Algebra of forms, of differential forms, with the exterior product on a manifold. But here we consider them as something abstract. Okay. Okay, so now here comes Berezin calculus. Berezin calculus. So we would like to define those general element of the algebra as a function of the thetas and the theta bars. Can we look at, can we consider G viewed as a function, let's say a polynomial, in the thetas and the theta bars? And considered as a function, can we define operation on those functions? Because this is just an algebra. So can we define a derivation operation? It's going to be a formal operation that I'm calling derivation, okay? So I'm going to define a derivation operation by taking that the derivation with respect to a generator theta I is going to be 0 if it applied to a real number, because a complex number to a complex, yes?
Is this G the same as the above?
It's any G,
Okay.
any element of C, I'm sorry, of the Grassmann algebra on G, and you can view it as a, so it's a linear combination of the thetas and the theta bar, but you can view it as a polynomial in the theta and the theta bars, which are anti-commuting numbers. And therefore, you can think of it in terms as a function of the thetas and the theta bars. Okay?
I was just thinking whether you take the coefficient as functions over zero.
No.
Just numbers.
No. Okay? So let me define a derivation operator, but I state that if make the derivation with respect to theta I of a complex number is 0, okay? And the same for any theta bars, okay? And I define that data of theta i's with respect of another theta g is delta ig. So if I make a derivation of one variable with respect to itself, this is 1, and elsewhere it's 0, okay? And the same for the theta bars. Of 1 is 0, d over theta bar of I of theta bar of g is delta ig. So this is 1 if g is equal to I and 0 otherwise. And I define that the derivation with respect to theta I of theta bar g is always 0. So d theta bar of I of theta g is always 0. So this looks like the ordinary rules of derivation with respect to real of complex variables. Okay? Yes?
Does this definition include like the product rule of the usual there?
So I take this derivation operation for just generators. So this is the derivation operation. So this is the definition for generators. Okay? And for a general element, for a general product of G's, if I want to, so let me take a product of thetas and theta bars with some indexes here, okay? And I want to define what is d theta I of these products, okay? So I look for if there is an I here inside. Then the rule is that move theta I to the left, so that rewrite this as theta g, theta i's times theta bars. So you move this theta g you derive from to the left using anti-commutation rules, and then apply these rules. 1. And if, of course, you have no theta i's, then it's 0. If no theta I, this gives 0. Okay? And same for d over theta bar I. If you have a theta bar I, you move it to the left, but to the left of the theta bars and the theta, and you apply the rule. You see? Yes?
Okay, so when you mean apply the rule, that derivative was derivating the whole object.
Yeah.
That rules are just for one object. So yes. So when you say that we take it to the left
Yes.
and then apply that rule, we are implying some product rule for the derivative?
Yeah, see, with this definition, you are going to check that the derivative satisfies a product. So take this as a definition. Okay? So definition. So this is a definition, definition. Okay. So you see that in this operation you get signs. You just get signs. The only difference with only derivation for real number or complex number is going to be signs. Okay? So examples. So example, application, example. D over d theta of A plus B theta plus C theta bar plus D theta bar. This gives 0, this gives B, this gives 0, and this gives C, d theta. So this is B plus d theta bar. Okay? But d over d theta bar of A plus B theta plus C theta bar plus D theta bar is going to be C minus d theta, because you first have to move theta bar to the left and then apply. Okay, so you see this is a rule. Okay. Okay. So what is this operation? With this operation, with this definition, you can check that those derivative operation doesn't satisfy Leibniz rules, but anti-Leibniz rules. What does it mean? It seems simply that if you take the anti-commutators of the derivation with respect to two thetas, this gives 0. You see? The anti-commutator, namely d over d theta I of d over theta g plus d over d theta g times d over d theta I, this is 0. You see? And you can check that if I take the d over d theta bar of d over d theta of this, I get d. But if I get d over d theta of d over d theta bar of this, I get minus d. So it's just a consequence of the definition and of the anti-commutation of generators. Okay? And the same for d theta. So you have also that d over d theta I times d over d theta bar I g is equal to 0, and d over d theta bar I times d over d theta bar g, anti-commutator, is equal to 0. Okay? Okay. So this is for the derivation. So we have defined an operation. And now the second rule is that we want to define an integration operation. So we want to, can we integrate over function over some variables of some function? Okay. Okay. So I want to define an integration operator that I'm going to define integral over d theta I and integral over d theta bar I. Okay. And here I'm going to define it. I just want that this integration satisfies the integration by parts rules. So I want that integral over d theta I over d theta I. Well, for general functions, the integral of a derivative is given by just the boundary term. But if we consider an element of the algebra as a polynomial in the function of theta and theta bar are some abstract objects, so they have no boundary. There is no boundary. So I want this to be equal to 0, always. Okay? And the same for integral over theta I of, I want this to be 0. Okay? And the same for theta bar. This is what I want. Okay. And since the derivative operation, yes?
What does it mean to say there is no boundary?
Well, take it just as an image for stating that this property, I want this property.
Yeah, but I don't get the image of no boundary.
Okay, so then just take this definition. This probably means that it's a bad image. Okay, so I want this property to hold for theta and theta bar. Okay? Then, since the derivation operation anti-commutes, yeah. No, just take it. I agree. That's the way I view it. But you can just say, no, this is not a good way to think about this property. And then,
basically, we're working in like some high-dimensional complex space with a fancy structure on it. Huh?
yes, we are working on some. Well, we are working on a 4 times n dimensional space. We have defined a product, and we want to define some other operation, a derivation operation. Which
times n-dimensional space.
What?
Yes,
Yeah.
sure. With an explicit boundary by taking the complex.
No, I agree with you. So you don't like this image, don't take it, don't buy it. It won't change anything for the. No, just you know. Okay. So in order for this to hold, it's very simply to take that simply. When I say that I integrate over an element, I integrate over theta I some element of the algebra, it is the same thing that if I take the derivative with respect to theta I. Okay. Okay. So these are just a definition of an integration operation. Sometimes I'd like to think about the derivation as integrating over something. Yes?
You're saying that the second line is going to induce the first line?
Pardon?
Like the second?
Yes. No, but take this. So I take this. Because integrating d over theta I means taking d over d theta I twice,
Okay.
which is 0. So automatically this works. So this is the solution for this. Okay. Okay, so these are basically the rules that defines derivation and integration. Okay. So the first. Okay. So now, okay. So this I spent 45 minutes in defining some strand algebra, and now I want to show you how it can be used. It can be used to do Gaussian integrals and find a version of Wick theorem for anti-commuting numbers. Okay? So, what is a Gaussian? Let me take an A equal AIG, a complex self-adjoint matrix n by n. Okay, so this is just a numbers. Okay, I defined an element of the algebra, Gn, just as exponential of minus theta bar times the matrix A times theta, which means exponential of minus sum over I and G of theta bar I, AIG, theta I. Okay? And what do I mean by the exponential? I just mean the ordinary exponential. So sum over n, sum over k from 0 to infinity of 1 over factorial k minus sum over I and g and theta bar I, AIG, theta g, I'm sorry, k to the power k. Okay? Okay. So I take this as a definition of E. So to each matrix A, I define an exponential of the thetas and the theta bar A. So now, these are numbers, complex numbers. These are generators of the Grassmann algebra. So we get a product of A's and of thetas and theta bars. So now the rules, we re-express everything by putting the thetas to the left and the theta bar to the right. And you can see very easily that the only term k from 1 to n are present. Because as soon as you have more than n products, you are going to have necessarily at least twice the same theta or the same theta bar in the product, and it vanishes. Okay? So if k is larger than n, you are going to have some theta I, which is 0, and some theta bar I equals 0. Okay? So it's in fact the exponential, this sum is in fact a polynomial. This is in fact a polynomial. So it's a difference with ordinary number. Okay, so for instance, let's consider n equal 1. N equal 1. What is exponential of minus theta bar A times theta, where A is just a complex number, real number, in fact, because it's self-adjoint. This is just 1 plus A times theta, theta bar. Okay. Because the second order terms is 0. So it's, okay, and you can work out the example for theta 2. I'm not going to write the example for n equal theta 2, but it's, well, we can write it for n equal 2. So I get exponential, so I get a matrix A, which is A11, A12, A21, and A22. Okay? Well, it doesn't really need to be self-adjoint, but That's better, self-adjoint. Okay, and then this number A, exponential of minus theta bar A theta. So it starts with 1. Then you have two terms involving some thetas and theta bar. And what's interesting is the theta, theta, theta bar term. Because the theta, theta, theta bar terms is, so you get the theta 1, theta 2, theta bar 1, theta bar 2. And what you get is A12, A21 minus A11, A22. Okay. Do the calculation. Yes, sir. Okay. So now, let me define formally what is a, so this is substance the exponential of quadratic form. So what is a Gaussian integral? Gaussian integral for this. I start from A. And I want to integrate, to make this formal integration over the products from I equal 1 to n of d theta bar I times d theta I of exponential of minus theta bar times the matrix A times theta. Okay, so remember, this is an element of the algebra. So I apply this integration operation, and I integrate over all the generators. Integrate all the thetas and theta bars. Okay? So each time that I integrate over a theta, it's like a derivation. So one theta disappears. Yes?
What is the order of integration there?
The order doesn't import. It's not important because, of course, the integral anti-commutes, but the product of two integrals commutes. So if you want integral over d theta bar I, d theta bar g times integral over d theta, I'm sorry, theta I times theta I, d theta bar g times d theta g is the same thing as integral over d theta bar g d theta g times integral over d theta bar I times d theta I. So this commutes. So the order is not important. What's important is the fact that we integrate over the theta before the theta bar. So here it's important. Okay? Good. So now, well, let's do that for this. What you get when you integrate, when you have n equal 1, one generator, you just get A. When you integrate over two generators, remember, you integrate over, so let me assume, I integrate first over theta 1, but then over theta bar 1, and then over theta 2, and then over theta bar 2. So I have to bring back the theta bar 1 here. We give the minus factor. So for n equal 1, I get A. For n equal 2, I get minus this thing, so I get A11, A22 minus A12, A21, which is just the determinant of the matrix. And that's a general formula. So this is equal to the determinant of the matrix A for any dimension, general result. Okay? Okay? So this set of abstract rules are in some sense a way to write in an integral way how you write the determinant of a matrix. Okay, so it seems a bit complicated way to write the determinant, but it works. So this is for the Gaussian integral. Now let's define what is a 2 points correlation function, if you want, or a non-commutative cumulant. Okay. So I want to define what is the expectation value of G when I integrate. Okay. So let me define what is theta I times, well, let me use a second blackboard because it's, okay, no, I want to define what is the expectation value of theta I times theta bar G. So take this as a definition of what I call the expectation value of theta I. So this is going to be this Gaussian integral of products of d theta bar k times d theta k. Here I sum over k because the I and g are fixed indices and k. I get exponential of minus theta bar times a times theta. Okay? And I had here theta I times theta bar g. Okay, so I can do the same calculation. And, of course, I divide by integral products over k of d theta bar k d theta k exponential minus theta bar times a times theta. Okay. So it makes sense to divide an integral of anticommuting numbers by an integral of an anticommuting number because this is a complex number and this is a complex number. So it makes sense. In general, there cannot be any division operation in the Grassmann algebra because since generators anticommutes, they are nilpotent, so there are a lot of divisors of 0. So the algebra is not an algebra with a division operation. Okay, but this is complex number, so it's fine. So if you do the calculation, well, yes?
Can you repeat that last thing?
I repeat that the Gn, the Grassmann algebra Gn, the Grassmann algebra, so it is an associative algebra, but it is not what's called a division algebra. It's not an algebra with a division operation. So it's not an algebra with an inverse. Because theta bars, theta is equal to 0. So you cannot define an inverse for theta in general. That's okay. Well, that's a mathematical property of this algebra. You cannot define a division operation. So that's a fact, mathematical fact, mathematical property or lack of property of the Grassmann algebra. But these are complex numbers. This is a complex number. Okay. So now let's go back for instance. Oh no, I haven't done that, but you can do the calculation here. And you see that when you compute this integral, you have to take into account all the products of A, but the one that contains theta I, theta G. So in fact, you can get that this is equal to the minor Ig of the matrix A divided by the determinant of A. And therefore, this is just the matrix element Ig of the inverse of A. You see? So although this is not a Gaussian integral, although the integral of the differential form gives the determinant of A instead of 1 over the determinant of A for complex variable, when I compute the expectation value of the product of those two numbers, I still get the inverse of the quadratic form. Inverse of A. Okay? So that's some big theorem, that's all. But of course, if you compute theta bar of I times theta g, this is minus theta g times theta I. So this is not going to be the transpose. This is not to be the conjugate. This is going to be minus A minus 1 gi. Okay? Gi. Yeah, no, I'm simply interpreting that this is the same thing that minus theta g theta bar I. Okay? And then I apply my result. So it's minus. Okay, so that's what you need. You need to know that theta I theta bar g is A minus 1 Ig, and theta bar I theta g by anti-commutation is minus A minus 1 gi. Okay. Good. So this is the second result of the definition of my integral. And finally, well, let me just try this here. What happens if I'm taking the calculation of the products of four-point function? Okay. Well, it's easy to see that the only so this can be only 0. This kind of things can be only 0 if you have as many thetas and theta bars. Otherwise, it will 0. So you need to have as many thetas and theta bars. So let me try to compute theta I theta g times theta bar. I'm sorry, theta I theta bar g times theta k times theta bar L. Okay, so I compute by the same rule here the products of thetas and theta bars, but here they are in alternate order. So if you want to really write them in terms of the usual basis, you have to make anti-commutation of these thetas and theta bar. But let me take this. Okay. So then you have on the numerator a Gaussian, an integral with 2 thetas and 2 theta bars. So you are going to have in the integral a product of matrix element of A, but 2 of the matrix elements are missing. So it's a double minor, if you want. It's a minor where you have I and G. Well, you have A and K. You have G and L, and you eliminate these 2 lines and these 2 elements, and you compute minors of this kind. Okay. So the result is that the result of the calculation is that you get A minus 1 Ig times A minus 1 KL minus A minus 1 IL times A minus 1 KG. Okay, so that's the result of the calculation. So you see, this means that you have the minor when you are since you have removed these 2 lines, You have to take into account the fact that you can have this A missing element and this A missing element, or this A and this A missing elements. And you get this. And the sign minus comes from the anti-commutation. So it's just a result of the calculation. And you see that this is just using this result, the two-point function of theta I, theta G bar times theta K, theta bar L minus theta I, theta L bar times theta I, theta K, theta bar G. Okay? So this is a form of Wick's theorem. Because you see that the expectation value of the products of 4 thetas can be decomposed into a sum of the pairings of 2 thetas. But you have to pair theta with theta bar, and you have to take into account order the orientation. So if I write, for instance, the Feynman rules for this, I write that theta I, theta bar G is just a line going from the index I to index G. Then you see that these products, theta I, theta bar G, theta K, theta bar L, this 4-point function, can be written as Ig times KL minus IL times Kg. Okay. Here I have written an arrow because the arrow goes from the thetas to the theta bar. I have an arrow from theta to theta bars. So this is a Feynman diagrammatic representation for this operation. So you see that you get all the possible pairings between the thetas and the theta bar, but with a sign which is associated to the signature of the permutation. And this is similar to the minus sign in the Wick theorem for fermions. You see, which come from the anti-commutation of the creation and annihilation operator for the quanta of the Dirac field. Okay. So, Wick theorem for fermions is reproduced by these seemingly very abstract rules of integrating over anti-commuting generators of an abstract Grassmann algebra. Okay. Okay, so now I'm going to show briefly that with this kind of rule of calculation, it's very straightforward to define a fermionic path integral or functional integral for the Dirac field. Okay, so this is the second part of what I wanted to do today. Okay, so this is my 6th blackboard. Okay, so remember, what is the action for the Dirac field? So we have a anti-commuting. We have the Dirac field, and the action is d4x. I'm going to consider the free field, so no interaction, no coupling to fermions. So I'm just studying second quantization of Dirac. Second quantization the Dirac equation. And I'm in 4 dimensions for simplicity. So the action is psi bar of x, I, the slash derivative minus m times psi of x. Okay? So, well, here I am in Minkowski space-time, so I have a metric h mu nu equal minus 1, 1, 1, 1. I'm going back to the West Coast for because that's the standard notation for fermions. You have the gamma matrices, gamma mu, that satisfies the anti-commutating relation, gamma mu equal minus 2 h mu nu. Oh, no, I am in, I'm sorry, I am still in the West Coast, on the East Coast metric. But I am using the standard Dirac matrices so that the anti-commutator gamma mu and gamma nu is minus 2 h mu nu instead of 2 h mu nu, which is h mu nu of the West metric. So this is the East metric. East Coast metric. Okay, so that's the standard gamma matrix. Okay, and as usual, d slash is just defined as gamma mu d over dx mu. Okay. Okay, so in the first quantized Dirac equation, in first quantized equation, first quantized theory, psi and psi bar are component of a field. So psi is just denotes psi a of x, a equal 1 to 4, where a are the Dirac indices. Okay, and they are complex field. So psi a has a complex wave function of the component A of the Dirac field. Remember, the Dirac field has A component because it's a fermion, so it has a spin. And in addition, it has a helicity. Okay. So in the first quantized theory, of course, the psi a of x are wave function of a quantum object, but they are classical functions, are complex functions from the space-time to the real, okay, in the space of spinors. Okay. And it's in second quantization that you are going to replace psi and psi bar are going to replace by operators. Let's call it psi hat and psi bar hat. Operators acting on Fock space, on the Fock space. Okay. Field operators. Okay. Similarly, that in the Klein-Gordon equation, the first quantized Klein-Gordon equation, where phi is a wave function of a Klein-Gordon particle, becomes, in second quantization, a field operator. Dirac field operator here. Okay. Well, so remember, for Klein-Gordon, what we did was simply to replace the field of, so in Klein-Gordon, we have a field operator by hat of x, And in functional integral, we just realize this fit operator by a random variable phi of x, and we have a path integral of phi. Okay. So, can we do the same thing for the Dirac field? And the answer is very simple. The answer is yes. Well, I can keep this because it's here. Right? So, the answer is the following. The answer is simply replace each Dirac component psi a of x and psi bar a of x by generators of a very big Grassmann algebra. Okay, so now each psi a of x and psi bar a of x are generators. So I consider a very big Grassmann algebra, let me call it capital G, with generators, instead of being the theta i's and the theta bar i's, as psi a of x and some similarly conjugate psi bar a of x. You see? Yes?
For each x, there is a different generator?
Yes. So we had an algebra Gn with generators where theta I and theta bar I. And now we replace it by a big generators where the theta i's are psi and psi bar, which are indexed by x points in Minkowski's 4 space time. So it's already there is an infinite number of generators plus a going on for 4, which are Dirac indices. So but here they were indexed by I. Indexed by I, going from 1 to n. Okay, you see. So that's important. So in the same way that here, this random variable can be viewed as a random vector indexed by x. Okay. So it's an infinite dimensional Grassmann algebra. Okay? And here we have this Dirac action. Let me call it SD. So it's a Dirac action for the first quantized theory. And the equation of motion for the first quantized theory are Dirac equation. So equation of motion derived from the first quantized theory is Dirac equation for psi of x. Okay. So now let's just replace my quadratic form A, remember. Replace my quadratic form theta bar I aig theta g by a quadratic form in my Grassmann algebra, which is just the Dirac action S of psi bar and psi which is integral d for x psi bar of x I d slash respect to x minus m times psi of x. You see, so here. The sum over Ig is replaced by the integral over 4, and in addition, about the sum over Dirac indices. Okay. So the sum over I and G is replaced by the sum over I, let's say, is replaced by a continuous integral. Okay? And now let's define the analog of exponential minus s of phi by defining a fermionic path integral, a Grassmann path integral, which is just integral d of psi bar and psi exponential, well, I, the Dirac action of psi bar and psi. Okay? Where, as usual, this measure is just products over x, products over a of d psi bar a of x, d psi a of x. So the measure integral of a product of d theta bar I theta I is replaced by this. Yes?
Why are we ignoring the fact that there's two sums on the left and only one integral on the right?
2? Oh, that's because, as usual, this is a kernel of an operator. So, if you prefer, write this as integral dx. Well, let me write this. You can rewrite this integral d for x, integral d for y, psi bar of x. Yeah, it's an operator. So you have d slash x minus m, operating of delta of x minus y times psi y. And as a kernel, this depends on two operators.
So you're claiming that the specific matrix you need there
Yes.
is diagonal?
It's
diagonal?
no, it's not diagonal because of
Why
this.
would you have a delta on the right and no delta on the left?
Because the d slash operator is not diagonal. The derivative operator, you know. Think about a matrix. This d x is, if you want, an operator that's off diagonal. So you have a diagonal and you have the off diagonal here and the off diagonal here. So d slash is an operator which, if you take into account the fact that you have a lattice of your space and your time, and here you are I plus 1 and I minus 1, its matrix elements combines the value of the field at two different points. So it's not a diagonal.
You have two sums there over I and j, and they're
Yes.
replaced by integrals over x and y. You
Yes.
take everything on the left and turn it into something on the right, and
Yes.
suddenly there's a delta on the right. Where does it come from?
Now the delta comes from this, but you know,
It's like,
d slash x of delta of xy is not a diagonal matrix. It's not a diagonal kernel. This is not diagonal.
it's not what I'm asking.
Kernel.
You're making a dictionary between every object on the left and an object
Yes.
on the right. The sum becomes an integral. A becomes an operator. Theta becomes
Yes.
psi. Theta bar becomes psi bar.
Yes.
And suddenly there's one extra object. Where does it come from?
There is no one extra object.
There is a delta function.
No,
There's a delta function.
yeah, you ask me, well, some not you, but you ask me why there is one sum here. Why it should be written in terms of two indices. And I said, if you want to write it in terms of two indices here, Here you have a kernel K of x and y, which is given by this, which is a distribution which is not diagonal. It's exactly the same than for the scalar theory.
The presence of the delta function does somewhat suggest that this kernel is diagonal. In the sense
No,
that
because this kernel is not diagonal.
yeah, I mean I get that, but
Well, go back to what I explained for the scalar field. It's exactly the same problem, the same issue. Okay. Well, let's discuss that either after the course or at the beginning of next course, because then I want to end up with this. It's time to finish. So, okay. So you define this path integral with this quadratic form, and let's admit that it is not a diagonal. Then what you get just applying the rules, what we did for a finite dimensional Grassmann algebra. We get that the expectation value of the products of the analog of a theta and the theta bar, which would be a psi and a psi bar, we get it to be that the expectation value of psi of x, psi bar of y, and let's add Dirac indices, just by applying the rules. This is the inverse of the Dirac operator I d slash minus m, you see, between xa and yb, which is the inverse of a Dirac operator. So this is just the Dirac propagator between x and y and the matrix element A and B, okay? Which means that this is in Fourier transform integral d4p over 2 pi 4, and if I'm not mistaken is the sign, I divided by minus p slash minus m minus I epsilon plus, because by Quick rotation everything. So you take this matrix, you take its AB matrix element, EIP times x minus y. So it's just a consequence of what we did. So you get the correct Feynman propagator for the Dirac field. Just applying the rule, especially this rule. Okay? First point, and second point, when we compute some products of psi bar, psi bar, psi bar, etc., we get the Wick theorem for fermions with the correct sign factors coming from the anti-commutation rules. So for instance, if you replace theta of I, theta bar, and theta bar by psi and psi bar, you get that the products of a 4-point function, a vacuum expectation value of 4 fermions fields operator, is given by the combination of the two, given exactly by the same picture. Okay. So we are done. So, okay. So we are done. We have a functional integral. And canonical quantization. Okay? And the field operators correspond to Grassmannian fields, which anti-commute. Okay. Okay. So this will be important for quantization of Dirac fields coupled to gauge field. And this is going to be also important in the quantization of gauge field because of the fact that there appears what are called ghost fields, which are fields that obeys the Fermi-Dirac statistics, but spin zero, well, but spin integer, which appears in the quantization of the Abelian gauge theory, which obeys the Fermi-Dirac statistics, so they have to be represented by anti-commuting fields. Okay, thank you.